Hello, everyone. Today we're going to be looking at rotation of rigid bodies. This is chapter 9. It's going to be divided into two parts. And in part 1, I'm just going to be talking about rotational variables so that you can meet the players in our great drama of circular motion. And speaking of great drama, eventually you might be able to say whether or not this top is in fact still spinning or whether it stops spinning and whether we're in some sort of dream state or if we're in real world physics. So definitionally, a rigid body is a body that can rotate with all its parts locked together and without change in its shape. Now, real world rotations can be very complicated because bodies will stretch and twist and kind of move around or flex, much as, say, Sasha Cohen is doing here while trying to land a triple axel. But we'll assume for now that the axis of the rotating body is perfectly rigid. A fixed axis also means that the rotation occurs about an axis that is, well, fixed. That's why it's called a fixed axis. It's an axis that does not move. So we're not dealing with an axis that's wobbling or processing. Again, that's a little bit more complicated, and we're not going to worry about it right now. So in fact, let's enter the world of inception where that top is in fact spinning constantly without any particular wobble. All right, so the first thing that we want to do is define this idea of angular position. And angular position is defined by the quantity theta, and theta is measured counterclockwise from the x-axis. So this is positive theta going that way, and negative theta going that way. Again, this is by convention, and we'll be going over what that convention is or what that means in just a little bit. If we take a look at the distance of the arc, if we define that as s, and we say that the radius of the circle in which this particle or whatever it is moving, the angle between the radius and the arc is going to be theta. So we've got a radius here, we've got a radius here, the angle between the radii is theta, and that corresponds to some change in position s here. So if we're going to go ahead and define that angle in terms of r and s, we're defining that in an angle that is measured in radians, and theta is simply equal to the ratio between s and r. So it's s over r. You'll notice something kind of interesting is that radii are given in meters, and this arc angle is s, and that's also going to be in meters. So theta is in units of meters over meters, which means that theta is unitless, but which we call radians if we're dealing with circular motion or just kind of things behaving in a circle in general. And this makes some degree of sense. A full revolution, or 360 degrees, is equal to 2 pi radians. Well, why is that? If s is an entire circumference of a circle, the ratio between that circumference and the radius is 2 pi r. So it's pi is the ratio of the diameter of the circle to the circumference of the circle, and there are 2 radii in one diameter, so it's 2 pi radians is equal to 1 full revolution, and 1 radian is equal to 57.3 degrees, or 0.159 revolutions. When you're dealing with circular motion, in general, you want to be dealing with radians, because radians are unitless, and because radians are unitless, you can use them in a lot of very handy equations, as we're going to see in just a moment. So now an important public service announcement from Jimmy McMillan. You should remember that the number of radians in a circle is 2 damn pi. So keep that in mind. All right, so what about angular displacement? We've defined angular position as theta, and angular displacement, as you might imagine, is going to be delta theta. And if we're rotating from some reference position theta 1 to some reference position theta 2, delta theta is going to be the difference between these two particular positions, and its delta theta is equal to theta 2 minus theta 1. All right, that's pretty straightforward. And remember that an angular displacement in the counterclockwise direction is positive. So this is positive theta. And something that's in the clockwise direction is negative theta. Okay, so all right. So let's take a look at what exactly the angular velocity might be. Basically, what is the speed at which this displacement is taking place? Well, that's pretty simple. We say omega, which is what we define as angular velocity, average, z, we call it z because the angular velocity is actually perpendicular or is given as a vector which is perpendicular to the motion in the plane of the rotating object. So you'll sometimes see it as omega average z because the velocity vector for angular velocity is perpendicular to the object that is rotating. What is that defined as? That's simply the displacement, or theta 2 minus theta 1, divided by the time it takes to go through that displacement, time 2 minus time 1, or delta theta over delta t. So again, pretty straightforward. Units here are in radians over seconds. So this is here, delta theta is in radians, time is in seconds. So it's radians per second, but remember that radians are unitless. So that's simply 1 over seconds. 1 over seconds is sometimes written as seconds to the negative 1 power, which is also known as a hertz. So yeah, just remember that the truth hurts. And that was a really bad joke. I apologize. Anyway, units for angular velocity are in radians per second, or 1 over seconds, or hertz, or seconds to the negative 1 power. And a subscript z means the rotation is about the z-axis. It's perpendicular to the plane of the rotation itself. If we're looking at an instantaneous angular velocity, again, when you think instantaneous, you should think derivative. So that is the limit of this delta theta over delta t function as t approaches 0, or in other words, the first derivative of the position function with respect to time. So delta theta by, or d theta by dt. And when we refer simply to angular velocity, we mean the instantaneous angular velocity, not the average angular velocity. If I want an average angular velocity, I will ask you for it specifically. And here we're starting to get into that convention. The angular velocity is defined as a vector whose direction is given by the right-hand rule. So take your right hand, take your right hand, and then what you want to do is curl your right hand in the direction of the rotation. So let's say that the direction is counterclockwise, so it's going this way, and my thumb is pointing in the direction of the angular velocity vector. If the rotation is negative and it's going clockwise, then my thumb is pointing down, and that is the direction of the angular velocity vector. So we can see this here illustrated. Where you curl your fingers, and that's the direction of the omega vector. All right, and again, if you're going in the opposite direction, the omega vector is pointing in the other direction. It's very important to use your right hand when you do this, which is why it's called the right-hand rule. Go figure. All right, if the body's angular velocity is changing, that means that you have to have an angular acceleration, which we denote by the Greek letter alpha. So if omega 2 and omega 1 are angular velocities at time 2 and t and times t2 and t1, then the angular acceleration alpha is going to equal omega 2 minus omega 1 over t2 minus t1. So delta omega over delta t. And instantaneous angular acceleration, this should be kind of predictable by now. We take the limit of this function with respect to time going to 0. So this is the derivative of the angular velocity function gives you the angular acceleration. Note also that this is going to be the second derivative. It looks terrible when I try to draw it, that this is going to be the second derivative of the position vector with respect to time. So that would be d2 theta by dt2. So again, because it's the first derivative of the angular velocity, it's the second derivative of angular position. These relations hold for every part of that body, and the unit of angular acceleration is radians over seconds squared, or seconds to the -2 power, or 1 over seconds squared. Let's see what that looks like in practice. Let's say that we have a wheel here, and it's moving in the positive direction. It has a positive angular velocity, and that positive angular velocity increases. If that is the case, then the angular acceleration also has to be positive. And this is also determined by looking at the right-hand rule. So if we curl our fingers, again, in the direction of the acceleration, which is going to be in the same direction as the velocity, because the velocity is increasing, then we notice that this is going to be pointing up. And so in this case, that will be pointing out of the page and straight at us, would be the angular velocity. So it's really hard to see this on camera, but you can imagine if my hand is in the plane of the paper and I curl my fingers in that direction that the wheel is moving, my thumb is pointing straight at me. It's pointing right at my nose. And if we were moving in the other direction, oh Lord, then if the acceleration were negative and we had a clockwise motion or a clockwise acceleration, then my thumb would be pointing straight at the camera. It would be pointing into the page in that particular case. So what does this mean? Angular acceleration as a vector is also going to be perpendicular to the plane in which the rotation is occurring. And if the angular acceleration vector is in the same direction as the angular velocity, then rotation will be speeding up. So this is this case where the angular acceleration and the angular velocity are in the same direction. And if you have angular acceleration, which is slowing down this wheel, then the angular acceleration vector is pointing in the opposite direction to the angular velocity. And this actually kind of makes some degree of intuitive sense. So if you're taking a look at linear motion, if you had a velocity which is going this way, and that velocity is being decreased, what's that tell you about the acceleration vector? Well, that tells you that the acceleration vector is that way. That when the acceleration vector is opposing the velocity vector, the velocity slows down. Contrarily, if you have a velocity vector that's going this way and an acceleration vector that's also going this way, then the velocity is going to be increasing. So again, the rules are very similar to what they are in the linear world. It's just that you're now moving in circles. Now, I know that oftentimes when you're doing physics, you feel like you're moving in circles and spinning your wheels, but just remember that the angular world is actually not that different from the linear world. Okay, so some sample problems. Take a look at the sample problems on pages 275 to 277 of your notebook. But let's do, your course book, the textbook for this course. And let's take a look at another example right here. So the angular position of a point on a rotating wheel is given by theta equals 2.0 plus 4.0 t squared plus 2.0 t cubed, where theta is in radians and t is in seconds. At t equals 0, what are the 1, the point's angular position, and 2, its angular velocity, and 3, what is the angular velocity at t equals 4.0 seconds, and 4, calculate its angular acceleration at t equals 2 seconds. So let's just make the units explicit here, where we have 2.0 radians plus 4.0 radians over seconds squared t squared plus 2.0 radians seconds cubed over, times t cubed. All right, so there is the function. Let's do stuff to it. In part A, this is fairly simple. It's asking us for the point's angular position at t equals 0. So we just plug in 0 here in this function, and it's 2.0 plus 0, so 0 squared, plus 0, because it's 0 cubed, is 2.0 radians. Right? So far, so good. The angular velocity is simply going to be given by the first derivative of this position function. So omega equals d theta by dt. The first derivative here, what's going to happen is that this is a constant, so it drops out. This squared is multiplied by 4. So we have 8t, and then t cubed, this 3 comes over here. So 3 times 2 is 6. 6t squared, and that's going to be the first derivative, and that's going to be our angular velocity function, which we can evaluate at t equals 0, and we find that it's 0. 8 times 0 plus 6 times 0 squared is going to be 0, and that's omega naught, right? At t equals 4 seconds, all we have to do is plug in 4 seconds. 8 times 4 plus 6 times 4 squared is 128 radians per second squared, or hertz. And trust me, the units do in fact work out here. I didn't work it out, but take my word for it and work it out on your own if you really, really want to. But the angular velocity is 128 radians per second, or hertz, at time of t equals 4. So what's going to be the acceleration? That's going to be given by the second derivative of the position function, or the first derivative of the angular velocity function, and that's going to equal 8. So we take the derivative here, plus 12t, taking the derivative here, which again, we substitute, where we say t is 2, so it's 8 plus 12 times 2.0 seconds is 32 radians per second squared, and that's going to be your angular acceleration. Okay, pretty straightforward. Now, you may have noticed, and one thing that I've kind of been talking about, is that the angular world does look an awful lot like the linear world, just with different letters. You could say that in the angular world, it should all be Greek to you. Sorry, sorry, it's like a compulsion. Anyway, what this means is that the big 5 equations that we previously learned for an object that's moving at constant acceleration are also applicable in the case where we have a constant angular acceleration. Now, it's very important to note that this only applies when the angular acceleration is constant. So if angular acceleration is a function of time, forget about it, you can't use these equations. But if your angular acceleration is constant, then knock yourself out. There is a kind of a translation of the conventions here. So x, what we previously talked about as a position, is now given by theta. Velocity, linear velocity, has its equivalent in the angular world of omega. And a, acceleration, in the linear world has its equivalent in the Greek letter of alpha, that being the angular acceleration. And time is, well, time is still time. Yeah, so sorry to disappoint you there, but you know, there is no cool equivalent for time in the angular world. All right, so the constant alpha equations are analogous to the constant A equations in the linear world. So delta theta is equal to omega naught z times t plus 1/2 alpha z t squared. Omega is equal to omega naught z plus alpha z t. Delta theta is equal to 1/2 omega naught z plus omega z times t. Omega squared is equal to omega naught z squared plus 2 alpha z times theta minus theta naught. And delta theta is equal to omega z t minus 1/2 alpha z t squared. Don't get too hung up on the fact that there are all these z subscripts going on here. That's just to remind you that when it comes to angular acceleration, and angular velocity, those vectors are perpendicular to the plane in which the rotation is occurring. So if you want to see this in kind of a slightly tidier form, you can see all of these things which we previously studied. We saw that earlier. And again, all you got to do is think about what the analogous Greek letters are, and it will still work for you. So again, a good set of things to remember. All right, so let's take another example where we're trying to find what's going on in this particular situation. And I've got to hide, unfortunately, the floating meeting controls so I can read this. There we go. Sample problem, constant angular acceleration. So a flywheel turns through 40 revolutions as it slows from an angular speed of 1.5 radians per second to a stop. A, assuming constant angular acceleration, find the time for it to come to rest. B, what is that angular acceleration, which is constant? And C, how much time is required for it to complete the first 20 of the 40 revolutions? So if we're taking a solution here, we know what the wheel's initial angular velocity is. Well, we know omega naught. And we know that it's making this many revolutions per second. At time equals 0. And there's a constant value of angular acceleration. That value is going to be negative because the velocity is positive, and we know that this wheel slows down to a stop. So again, angular acceleration is going to have to be negative in this case. At t1, its angular displacement is theta 1 or plus 20 revolutions. We are defining that as let me just move this bar around. For part C, we say how much time is required for it to complete the first 20 of 40 revolutions. We're simply defining this as T1. And then we're defining T2 as equal to the point where this stops. Okay? And that's basically what all of this is saying here. T2 is where the angular displacement is plus 40 revolutions, and its angular velocity is omega 2 equals 0. So how do we solve this? Well, let's pick a handy-dandy analogous equation. Delta theta is equal to 1/2 omega naught z plus omega z times t. Okay? So first we want to obtain delta theta in terms of radians. We're told, and we're solving for time 2, we're solving at the time where this wheel has come to a stop. We're told that that is after 40 revolutions. But what's revolutions in terms of radians? Well, we know that the number of radians in a circle is 2 damn pi. So it's 2 pi radians equal to 1 revolution. And that's going to be 40 revolutions here. So we know that we have 80 pi radians that we're working with on the left side of our equation. The right side of the equation is 1/2 the initial velocity, which we're given as 1.5 radians per second, plus the final velocity, which is going to be 0, final angular velocity, which is 0. We're told that this comes to a stop. We plug all this in, and we solve for T2, and we find that T2 is equal to 335 seconds. All right? So any of the big 5 equations involving alpha can then be used to find angular acceleration. Again, we're allowed to use the big 5 equations because we are told that the acceleration is constant. So we have delta theta equals omega naught t plus 1/2 alpha t squared. You can use another equation, but I just liked this one. We know that this is 80 pi radians. Again, that's from 2 pi radians times 40 revolutions. And omega naught is 1.5. We know the time. We solve time t2 as 335 seconds. So we go ahead and plug that in here. And we say plus 1/2 alpha times 335 seconds squared, and the squared should be outside of the brackets, but I think you know what I mean. We go ahead and solve. And when we solve for alpha, we find that it's equal to negative 0.00448 radians per second squared, which we can convert into scientific notation as negative 4.5 times 10 to the negative third radians per second squared. So that's 1, 2, 3, and we go ahead and round that off. Okay, now that we have T2 and alpha, we can go ahead and solve for T1, or sorry, we can go ahead and solve for, let's see, how much time is required for it to complete the first 20 of the 40 revolutions. So we can now solve for T1. So theta 1, in this, using this equation, we know theta 1 is 2 pi radians over 1 revolution times 20 revolutions, because we're trying to see how much time is required to complete the first 20 of 40 revolutions. We know our initial velocity times T1 minus 1/2 0.00448 radians per second squared times T1 squared. The reason that this is minus is that our acceleration is negative. So if we take this quantity and we plug it into this equation, then we're going to see this minus. Okay? So now we have a nice quadratic equation. We can rearrange this to our heart's content. And we're going to eventually find, if we use the quadratic formula, that there are 2 positive roots, 98 seconds and 572 seconds. Well, we're told in the problem that we're being asked for how much time is required to complete the first 20 of the 40 revolutions, meaning that time 1 is going to have to be less than time 2. I mean, that just makes sense. You know, you're not going to complete 40 revolutions and then complete only 20 revolutions. So when we have our 2 positive roots, we say it's 98 seconds. It's the smaller of the 2. Okay, just remember, it's not always going to be the smallest of the 2 in every problem you ever do, but make sure that you take a look at the context of the problem when you're solving these quadratic equations and say, do I use the plus or the minus form when we're going ahead and solving it? Okay, so yeah, again, keep that in mind. Make sure to use your head whenever you're using the quadratic equation and you get 2 possible answers that pop out of it. Okay, public service announcement. But most of the time, you know, if I'm sitting on a merry-go-round or a Ferris wheel or you know, I'm swinging a heavy weight over my head just for fun, you know, if I'm trying to relive David and Goliath, you know, or trying to be a slinger or something like that, I'm not necessarily interested in what the angular velocity is going to be, or what the angular acceleration is necessarily. I'm more interested in what am I feeling when I'm a particle that's on the edge of this particular circular path. Okay? So how exactly are we going to interrelate what the particle is actually feeling and the angular velocity and angular acceleration? Well, the position is going to be given by theta times r. That's fairly straightforward. You know, the arc that you make is going to be larger depending on how far away from the center of the circle you are. Oh, that makes good sense. Remember that you want to use radians and not degrees. So again, I'll say that again, use radians and not degrees, okay? If you differentiate this with respect to time, and you say that r is held constant, so why are we holding r constant? Well, if we're measuring the velocity of a particular point, you know, as it's moving around this circle, the distance between that point and the center of the circle is fixed. It's not going to vary with what angle you've got, or it's not going to vary with speed. It's going to be fixed. So if we differentiate both sides of this with respect to time, and we hold our constant, that means that ds by dt is equal to d theta by dt times r. And we'll notice something kind of interesting. What's that? What's ds by dt? Well, that is the change in position with respect to time, which we all remember as velocity, right? And then if we've got this derivative of the theta function with respect to t, that's going to be the angular velocity. That's going to be omega. So v is equal to omega times r. All right. So that's kind of a very handy sort of interrelation. Or if you want kind of a more intuitive explanation or a more straightforward explanation, I'll let Bill Waterston provide that for us in a Calvin and Hobbes strip, where Calvin's dad is saying that if you compare a point on the label in the very center of this record with a point that's on the outer edge, you'll notice that they're making a complete circle in the same amount of time, but the point on the edge has a greater distance that it actually has to cover. So in a way, you have 2 points that are moving at 2 speeds, even though they both make the same revolutions per minute, which sort of blows Calvin's mind here. But had Calvin taken his physics class, he would have pointed out that the speed of the 2 points is not the same. The angular velocity is the same, but the linear velocity is dependent on radius, as illustrated by this record. Of course, I might be dating myself here, or labeling myself as a hipster by saying that I've actually observed this in action. So if you have a record player, I recommend that you kind of check this out. And if you don't know what a record player is, think of it as an analog MP3 or an MP3 that's moving in a circle. That doesn't make any sense, but it's the best I can do. All right. So let's, again, try to put this all sort of together. If we're talking about the period of revolution, t, so how much time does it take to complete one revolution of the circle? That's going to be, well, the velocity, the straight velocity, the straight line velocity, is equal to 2 pi r over t. So 2 pi r, you might note, is going to be the circumference of the circle over the amount of time that it takes to go around that circle, and that's going to be equal to the velocity. So the period, if we rearrange this, is equal to 2 pi r over v, over the linear velocity. But we saw on the previous slide that v is equal to omega times r, omega times the radius. So when we plug in, we find that t is equal to 2 pi r over omega r. The r's will cancel, and the period is given by 2 pi over omega. So that's another kind of handy thing to have in your back pocket. So it's, as you might imagine, the distance that you have to cover, 2 pi, over the speed at which you're covering it, gives you how much time it takes to cover one full revolution. All right. If we differentiate our velocity function, dv dt equals d omega times dt over dt, again, holding the radius fixed. Again, radius is not going to be a function of anything else that's going on here. We find that the linear acceleration, or sorry, not the linear acceleration, the tangential acceleration. I caught myself there, and I'll explain why it's very important I caught myself there. The tangential acceleration is going to equal the angular acceleration times the radius. Note that dv dt equals at represents only the part of the linear acceleration that is responsible for changes in the magnitude v of the linear velocity, responsible for changes in the magnitude v of the linear velocity. Like v, that part of the linear acceleration is tangent to the path of the point in question. So if you are actually moving at a constant velocity around this circle, if the velocity does not change, then the tangential velocity is going to equal 0. All right, so keep that in mind. All right. So again, if you're not seeing any magnitude in the velocity change. So we have three different accelerations that we're dealing with here when we're talking about looking at a circle. There is the tangential acceleration, and that's equal to r times alpha. And then you have the velocity, which is r omega. These are in the same direction. And again, if this magnitude v is not changing, then a tangential is going to be equal to 0. There is the radial acceleration, a radial, which is equal to omega squared times r. This, as you might imagine, as you might remember, is the centripetal acceleration. That's the acceleration directed towards the center of this particular circle. And the linear acceleration of point P is equal to the vector sum of the tangential acceleration plus the radial acceleration. And how can I say it's the sum? Well, let's say that we got the tangential acceleration. If we move this vector over here, you'll notice that that's tip to tail. These are additive. Or, if you prefer, if we take this radial acceleration vector and we move it over here, that's also tip to tail. These add up. Okay? So again, there's a very important distinction to be made between tangential acceleration, radial acceleration, and linear acceleration. And I really want to bang on this because everybody got this wrong on the last homework, almost without exception. When you're dealing with uniform circular motion, in other words, motion at a constant velocity, then indeed your linear acceleration and your linear acceleration and your tangential acceleration are going to be the linear acceleration and the radial acceleration will be pointing in the same direction. But if you're not dealing with constant velocity on the outside here, the linear acceleration is going to be, again, the sum of the tangential and radial accelerations. Okay? And what does this mean? What do each of these things mean? Again, the radial acceleration is the acceleration that is holding this particle in this circular motion. The tangential acceleration would be changing the velocity or changing the magnitude of the velocity. And the linear acceleration is what is bending that velocity vector as it goes around the entire circle. Okay? So remember, three very distinct forms of acceleration here. Tangential, linear, radial. Take a very close look at this particular diagram. All right, let's go ahead and try to tie this all together. We're given a problem where an astronaut is being tested in a centrifuge. The centrifuge has a radius of 10 meters, and in starting, rotates according to theta equals 0.30 t squared, where t is in seconds, theta is in radians. When t is equal to 5 seconds, what is the magnitude of the astronaut's A, angular velocity, B, linear velocity, and C, acceleration A? The angular velocity at t equals 5 seconds is, again, we remember that the angular velocity is the first derivative of the position function. And so that's the first derivative of 0.30 t squared. And we go ahead and execute that. We plug in for 5 seconds, and we find that it's 3.0 radians over seconds. How about the linear speed? Well, we know that the linear speed is simply omega times r, or 3.0 radians over seconds times 10 meters, which is the radius that we're given, or 30.0 meters per second. And note also, because radians are unitless, we have a meter here, meters per second, and everybody's happy. The angular acceleration is going to be the second derivative of the position function, or the first derivative of the angular velocity function. So 0.60 t, we do the acceleration here, we find that it's 0.60 radians per second squared. So incidentally, because the angular acceleration is constant, we can use the big 5 equations if we wanted to. Right? The tangential acceleration, AT, is equal to alpha times r. So that's 0.60 radians over seconds times 10 meters, or 6.0 meters per second squared, right? The radial acceleration, a radial, is equal to omega squared r, or 3.0 radians per second squared times 10, or 90 meters per second squared. And then to find the total acceleration, what we're going to have to do is, if we're looking at linear acceleration, we know that this is a vector sum. We know that we have two sides of a right triangle here. So we have a tangent here, a tangential here, a radial here, and we've got a right triangle. So what we can do is use the Pythagorean theorem. And then what we say, or alternate, yeah, we use the Pythagorean theorem. So a sub t squared plus a radial squared equals a squared. Go ahead and plug and chug, evaluate, and you find that the acceleration is equal to 90.2 meters per second squared. All right, that concludes part one. In part two, we're going to be talking about the moment of inertia, which is where we find that not all objects are created equal in terms of how they move or how they rotate. And we'll understand the why and wherefore in our next lecture. Thank you for watching, and I will see you next time.